up, please. Let's get started. You guys act like come back from Christmas break or something.
Christmas break's only a week.
Well, I know. All right.
Not even that exciting.
All right. You won't even have missed each other yet. All right.
Spring break is longer.
So, quiz tomorrow. Two tracks of problems that we talked about. One track is what? The chart stuff. Finding inflection points, local max min, global max min, which would involve a list of candidates, the chart stuff, local max min, that kind of stuff. Flex points involves the number line. All involved, of course, doing derivatives, setting them equal to 0, maybe second derivative, setting equal to 0. Those kind of questions. Of course, that would also be, I guess we've got those two tracks, and then there's kind of an overarching thing over top of all that, which is doing derivatives using those shortcuts, those derivative rules. You know, the derivative rules is a part of kind of all of them, right? So if we were going to talk about the things that would be on the quiz, okay, which is really from sections 4 through section 7. Okay, then rather than just break it down into sections, because as we've noticed here, our homework has been kind of, mixed throughout all of the sections. What really separates the sections is what type of function are you dealing with. In section 6, it's mostly exponential and log kind of questions. In section 7, it's mostly trig kinds of questions. In section 4, it's mostly polynomial kinds of functions. And then, of course, section 5 then is when we talked about this other track, and the other track was what? That was the differential equation. Okay, now of those two tracks, which one do we want to spend more of our time today working on? Differential equations. Raise your hand if you would vote differential equation. Okay, all right. Now, so one thing then obviously would be the derivative rules. We'll practice a few. I'll throw a few of those at you. And then, of course, antiderivative, which is really just kind of that in reverse. I hesitate to say antiderivative rules, just being able to do antiderivatives. We do kind of have one antiderivative rule, which is the power rule, where you raise the power up 1 and divide by the new power. But really what an antiderivative is, the rule for antiderivatives is find the function so that when you do its derivative, you get back to the original function, okay, the one you're starting with. Okay, that's how you do an antiderivative. So when I have x to the third, the reason that 1/4 x to the fourth is the antiderivative is because when I do the derivative of 1/4 x to the fourth, I get x to the third. And then always keep in mind, whenever you do an antiderivative, you always have to tack on plus c. And that goes back to chapter 1. When you have an f prime graph that you're starting with, so those are the slopes of the function. There could be a lot of different functions that all have the same slopes. They would all be vertical shifts of one another. Okay? So anytime you start from f prime and go back to f, you're going to have these vertical shifts, or this plus c, this unknown constant. And of course that came into play with differential equations too. You have these unknown constants, and that's this idea of IVP that people have been asking me about. Initial value problem. All that is a differential equation, because remember, differential equation means you start with a derivative. It's got a derivative in it, and you want the original function. So it kind of involves antiderivative sometimes. And there's going to be this plus c or some unknown constant. And so to find that constant, you need to know some point on that original graph. You need to know some value, and usually you just plug it into the equation, and that helps you find the c. Okay, so there's a connection there between those ideas. All right. So you're going to have problems where here's F, you have to find F prime. And you're going to have some problems where here's F, and you're going to have to find big F. Okay, so you're going to have to do some of those. So we'll practice a few of those here in a little bit. Okay, second thing would be, of course, the differential equations. And along with that is the IVP, which is the same thing. Remember, IVP is just a differential equation with initial conditions. An IVP is just a differential equation with initial condition thrown into it. And the initial condition's only there so you can find the unknown constant, the plus C, or whatever. Of course, with differential equations, we had, I don't think you need to go back and rewrite all this. Let me show you on the screen here. Okay, we had, okay, so there was our, I mean, this is all in your notes. I don't think there's any sense writing this down all over again. Differential equations, equation that contains one or more, it should say one or more. An equation that contains one or more derivatives. There we go. Oh, now it's gone. Oh, well. There we go. All right. One or more derivatives. In other words, we had a y prime and a y double prime in it or whatever. The solution to a differential equation is the original function, f equals or y equals. So that's, again, some of you, I think, were getting hung up in some of the homework where it said solve it, and you're wanting to come up with an answer like 7. Okay, that's not what happens when you solve a differential equation. You get another equation. You get y equals something that's an equation. It's got x's in it. All right? We said there are 3 types. We said there are 3 types of differential equations. There's a type that we can easily solve by doing an antiderivative. Okay? Now, this is a differential equation because I did not put an initial condition with it. If I put an initial condition with this, like, for example, if I would have taken this problem, let's just work this one real quick. Actually, I'll have you type in your calculator. We'll see how we do. If I gave you this differential equation and I told you f of 1 equaled 7, okay, that's an initial condition. So now I've turned this differential equation into an initial value problem. Right? I gave you a differential equation with my initial condition, and I said to solve it. Well, I've already done the hard part for you. I've done the antiderivative. This is called the general solution to the differential equation right there. Now I want the specific solution. Okay, so just take a second and do that. Take this initial condition along with that solution I just got on your paper. Just figure out what the specific solution would then be. Okay? And I want you to type that into this poll question on your calculator. Okay. Now it's a blank, it comes up on your calculator as a blank poll, but where in the line where it says f of x equals, I want you to type in the specific solution. Don't make this harder than it is. This is an easy question. Other than it's got some fractions in it or something, maybe. Make sure you submit. Make sure you go up and submit your answer. Now, I'm getting some people, I'm getting a few answers where you just have a number. Okay, I'm getting a few people who have 3.5 or 3.5 or 7 halves as their answer. And this is where, this is what I'm talking about with the confusion of what a solution is. I want the solution to the differential equation. What should that be? What should that look like? A function, right? The solution to a differential equation is the original function, y equals or f of x equals. Those of you that are giving me 3.5 as the answer, what are you giving me? What c is, right? And it feels like a solution, right? I mean, that's what we're used to in algebra. C equals 3.5. Now, for those of you that are not sure where they're getting the 3.5, help us out. Everybody that's getting the 3.5, what do? I put 1 in for x, and I put 7 in for the f of x, or the y, the output, right? So, for right there, I put 7, 3 halves, 1 squared, 2 times 1, plus c, and I solve that for c. So all this time in the last 20 minutes, I've been saying, or however many minutes it's been, I've been saying, find c. Take your initial condition and find c. This is what I meant. This is how you take your initial condition and find c. You take your general solution that's got the unknown constant in it, and you take and put the 1 in for the input variable, and you take the 7 and put it for the output variable. So you get 7 equals 1.5 plus 2, that'd be 3.5, plus c, you subtract. You know, the people watching the video are not seeing this, are they? Oh, well. So, I just realized that. But everybody's here. So you guys won't have to watch the video. But you might want to review. But anyway, we get c equals 3f. But we're not done. Feels like we're done, right? We did this in algebra, stuff like this. You were done when you got to this point. We're not done. The general solution then says take the 3.5, put it back there for c, and our answer is, as many of you put here, so the answer is 3 halves x, f of x equals 3 halves x squared plus 2x plus 3.5. Okay? Now, somebody down here's got this, but looks like they've got 3 times a half. On your calculator, when you type in 3.5, you either have to put 3.5 or you have to put 7 halves. I don't think you can do a mixed number just like, because 3.5 is not 3 times a half. 3.5 is actually 3 plus a half. Okay, so if you type in 3 plus a half, you'd have. Okay, I'm not sure why. Oh, this person got it wrong because they didn't put x squared. This should have been 3 halves x squared. We can. Who did it? Josie. Okay. Now this person put the 1 in for x. We already had the 1. We put the 1 in for x to find the c. But when we go back and put it now into the function, we want to put it the x's back in, and we want to write that solution. Okay. So it does. It's pretty cool. That's what I like. That's what I like about this. Notice the box here. What this means is I think these people had one type of solution. These didn't have. Like the clickers, you know, we can text with the old clickers and stuff, and we can put stuff, but they have to be an exact match. Here, because of the calculator engine that's inside here, whatever you typed in, if it was equivalent to this, because it could simplify it and tell, then it puts you in this category. And that's what this box was here. I think these people... What did those people have? You put 3.5?
Exactly.
So I think that group put 3.5, and this group, did you guys put 7 halves? Did you guys put 7 halves? Okay, so I'm guessing that's what what that was about. Okay? All right. Very good. All right. Now, all right, so that is what we just went through there was solving an initial value problem. Solving an initial value problem. Now that's assuming that it's a type 1 differential equation. The type where we can just do the antiderivative. Well, this one was because it just had x's in it. Now that's the key. If you go to the second type, which we said was the one that we're going to memorize it, you can't do the antiderivative. Here I put an example here. This was like number 47 in the homework the other day with the First National Bank and the 8% interest. Here I did one with 4%. If I give you this differential equation right here, then you go directly to this solution. You can't try to raise the power up 2. You can't do that with p as the variable. That's the output variable. You can only do antiderivatives with respect to the input variable, with respect to x or t. Those are the two input variables we almost always use. When you see one that looks like this, y prime equals ky, remember our output variable is always the one that has the prime on it. We always do f prime or y prime. Okay? Our output variable has a prime on it, and the output variable also shows up inside there. We can't, it's not a type 1. We can't do the antiderivative. All right, but what we've said is we'll just memorize this is the exponential differential equation. It's the one that has this as a solution. Now, of course, if I have a 0.04 right there where the k is, then that goes right there. Now my unknown constant is the a. So again, if I gave an initial condition on this one, which I think in our homework they told us this was a bank problem and you had 4% interest. And you were initially going to put in $2,000? It said you're going to initially put in $2,000. Well, that's like saying P of 0 is $2,000. So we would put a 2,000 right there. We would put a 0 in there. Do you see how that's the same thing we were just doing in the last problem? Put a 0 in for T, put a 2,000 in for the Y, the output. And of course, this is pretty easy when e to the 0 is 1, so we find a to be 2,000. But we're not done. I didn't say find a. I said solve the differential equation. So what do I write? P equals 2,000 e to the 0.04 t. So I always want to end up with y equals or f equals or p equals with just the input variable in it. Right, if I can. Now, if they didn't give me this initial condition, then I'd have had to stop here. This would have been the best I could do. That's the general solution. It's got an unknown constant in it. Did you notice that series of homework problems where they kept saying, how many solutions are there? Remember those problems, number 5, number 6, number 7? How many solutions are there? What they were trying to get you to think about there is that if it's the general solution, how many solutions are there? Infinite, right? So I think some of you weren't maybe quite catching on with why they were asking that all the time. It was really a simple question. You weren't supposed to be counting up solutions. If it's a general solution, there's an infinite number of solutions. If I give you an initial condition, how many solutions are there? One solution. Now, I had this conversation with a couple people. They said, well, wait a minute. There's a lot of solutions to this. I could plug in anything I want for t and get out something different for p. Okay, what are we confusing there? Well, we're confusing the solutions to the differential equation with the solutions to this function, right? Yes, this function has a lot of different solutions to it. You know, after 1 year, I'd have how many dollars? After 2 years, I'd have how many dollars? Okay, but that's not the solution I'm talking about. I'm talking about the solution to this differential equation. Okay? Its general form is this. There's an infinite number of these because A could change. But if I give you this initial condition, there's one solution to the differential equation, and here it is. Okay? Here it is. That's just the single solution for that initial value problem. Okay, so that's what was going on there with those differential equation problems. Sometimes some of this doesn't all start to make sense till you've struggled your way through it for 2 days or so, and then you can start pulling together the different questions that you have. Okay, hopefully that's what we get accomplished today. All right, and then we have this third type of differential equation, and that's the type that we don't know. We can't solve a differential equation like this. We'll have to be given the solution. Like on number 11, they said, see example 5 of today's homework. Number 11 said, see example 5. Or maybe that was 2 days ago, I can't remember. Well, you got to go back to example 5 in the book, and in there they told you the solution. Y equals square root x plus c. Right? They told you what the solution was. And what you could do with that is then verify that it is the solution. Or maybe they give you an initial condition you can plug in and figure out what C is. Okay, so here I just went through an example and I said, okay, is 3x to the 4th, y equals 3x to the 4th the solution? If it is, I'll plug a 12x cubed in for y prime, I'll plug this in for y double prime, and I'll check it and see if it's a solution. And that's this thing we call the T-chart. Is it a solution or not? Do the two sides equal? No, they don't, so it's not a solution. Okay? So those are the things we had. Let me see what this... No, that's not. All right. So back to this part on the quiz here. So, all that stuff with differential equations. Being able to do those things. Mostly, well, that was in all the sections. Remember those problems were in section 5, section 6, section 7. All right. And then the third thing would be all the chart, which would be local max min, or we call that extrema. Local extremas, local max min. That would be inflection points. You know, that'd be increasing, decreasing, concave up, concave down, all that stuff. It would be global max min. That's not really from the chart. That's where we do our list of candidates. Now remember with the chart stuff, that's where we do number lines. Typically number lines are what help us do that, because that's, we can find out where our stationary points, where our possible inflection points are. Global extreme is more of a list of candidates kind of thing. Okay, that's pretty much it.
Can we do a practice one of those?
Absolutely. The chart one, that's what we're gonna do right now. We're gonna do some different practice ones of these various things. Let's start. And then we'll see if through this practice it might answer some of your homework questions. And we'll kind of do this backwards. We'll come back and do some of the homework questions towards the end, some of the specific ones. But all right, so let's do this. Let's go. Let's start at the top here. Let's do a little bit of practice. Now, I'm going to send you that same quick poll question. I'm going to send you that same poll question. And in that blank, it said f of x equals, okay? But this won't necessarily be f. Like, I'm going to give you a function here and tell you to do the derivative. Okay, so you're really going to be finding f prime. But on the calculator, you'll type it in. Okay, even though it says f of x equals, don't just ignore that, okay? Just so we can see how we do. All right, number 1. All right.
Wow, that's really messed up.
Yeah. All right, let's go. 3e to the 2x minus 4 minus 4 cosine negative x plus 5 to the x minus cube root of x squared. Okay?
Could have been easier. Antiderivative or?
Find f prime of x.
Oh, God. I don't know.
This, of course, would be no calculator.
Of course.
Okay? Of course.
Why would it be? What was that? Are you gonna send out the protocol?
What?
I did.
It raised.
You sent it out and then it disappeared.
Oh.
Then it disappeared.
I saw it because I picked up my calculator.
Okay. All right. How about now?
Shouldn't it be f prime of x?
Are you, that's what I was just saying. That's what I was saying a minute ago.
Is that messed up?
No, I just made one blank one to just send out to you. It's always going to say F, so just
Just deal with it.
just deal with it.
No, you didn't do this, Jared.
You're right, that's right, Harry. Because look, Harry, look. Yeah, can you put this right with this instead? Can you put that in front?
You're not okay.
But you're going from two trips. I'm not comparing with you.
I've got. I don't have one single person that agrees with another person yet. I got 10. I got 10, 10 submitted and 10 different answers. Now I'm getting a couple that are like.
Hey, did I agree with anybody? Did you type it in already? Or what'd you get? Read yourself first. 6 cents. You need to look at this.
Let's do two of them.
6.
The derivative of e to the x is e to the x.
All right. Now, if you've got that one, I'm not going to send the poll out, but some of you are still typing. That's fine. If you've got it already entered, now you can start on this next one. And then we'll come back and check it. We'll shorten it just a little bit here.
Blank, twice the blank.
Yeah, so one by one.
Down one.
Yes.
Yeah. Oh wait. Oh yeah, I got confused with something else.
Okay. Try this one.
What'd you get for the last one?
Oh wait.
You're gonna make it more hard.
30x.
Minus 2/3 x
Plus
negative 1
X.
Oh,
plus ln2. Let's add a third one on there.
Are you going to give us
Really?
these answers eventually?
Uh-huh.
Don't complain.
I will complain.
Okay, I'm
Don't
happy
doubt me.
you have some.
I wasn't doubting anything, I just asked you not to complain.
Just what I'm not gonna show you.
Are these the kind
Hope not.
Yeah.
Uh,
Maybe not all those. Maybe not all those all in one. But
I'll be gone
one like number 1 would probably be worth 4 points. I would give you one for each. You got to do the derivative of 4 different things there. So it's not like if you missed one of the 4, you would lose all the credit.
You get
One over 4x plus 1 over x times 1 over ln 3.
Oh yeah.
Yes, doing it now.
I'm very proud of myself.
Oh, are we starting?
Yes, I'm pretty proud of you.
That's just that funny getting calls.
Whoa.
Yeah, it's just
Ah.
Like the comments we did. Well, that
All right. Okay, listen up now. Listen up. Let's try these because then we have to do the antiderivative. And those are hard.
Oh. Those are nice.
All right. So listen up here now. All right. What is it? What do we do when we've got a 3 sitting outside? Just hangs out there, right? What's the derivative of e raised to? Well, what's e to the x derivative? E to the x. But what happens when there's a 2 on the inside? Whenever there's a 2 or any number multiplied on the inside of a function times the x, it has to come out. But what about inside? It stays inside. The inside always stays the same. So what should we have here?
6 e to the x.
6
2x. Sorry.
e to the 2x. Okay, now, there were a number of people who our most popular answers.
Who did the threes?
The first 2 here forgot
See who
the first 3 series. Forgot those. Okay, well they know who they are.
Which was
Okay, now we got a series of them that have the 6. Now I got a couple people who did 6e to the x here instead of the 2x. Now maybe on your paper you had it right, just typed it wrong, maybe. Okay, but looks like we got a couple here. Here's the order's a little different, so there's one, so maybe we're good yet. Now, okay, so the -4 is just going to hang out there. What's the derivative of cosine? Negative sign, so that's going to turn that into a positive. But wait a minute, there's a -1 multiplied on the inside. So it's going to kick out to the outside as a negative. So we had a minus. The derivative of cosine is negative sign. We're going to have to kick out a negative. So it ends up being negative anyway. For sine and the negative x, the inside always stays the same. All right. So we should have a -4 sine x. So this group here has it. This one has, or excuse me, negative x inside. Except they had that 6 thrown in. That looks right. What's the derivative of 5 to the x? 5 to the x times ln 5. Right? That's just like e to the x, but you have to tack on that extra thing. So they've got it. This one's no good here because they divided by it, which is actually what we do on the antiderivative. Right? When it's the antiderivative, we would do that. All right. And then, of course, cube root, this is x to the 2/3. So when we divide by 2/3 there, I should go back to this just in case somebody later wants to look at this.
Okay, I just fixed it.
Okay, this should be minus 2/3 x to the -1/3. Okay? Which it looks like this one is right here. No, but that was wrong with the e to the x.
That one is right.
It doesn't have a negative on the 2/3.
Who did that one?
We should have negative 2/3.
I work so hard.
With the totally Tyler so. Could the sine part be right if you had plus 4 sine of positive x?
What's wrong with the one above that?
This one doesn't have a 2x in there. Derek asked a good question here. Sine is an odd function. So sine negative x is the same as negative sine x. And your calculator a lot of times will make that substitution. So sine negative x could be replaced by a negative sine x. So if you put just an x here and a plus here, that'd be okay. Okay? And that, it should have taken care of that, probably.
So I just forgot the negative.
So,
2/3.
do we still have any of these that are right?
How do you know which number to take out?
Ouch.
But go up, go up.
Uh-oh, here's some people who wrote e to the 2x minus 1, subtracted the power. See, another good thing about this is we can see the common mistakes that we're making. It's not a power rule with e to the x. It's not a power rule with 5 to the x. Only on x raised to a number.
Disturbing us.
Hey, what about that one?
This one has a plus on the 4 sine negative x.
Okay, different.
That one has a plus.
That one.
What's that?
What the one right there? That one looks like it's No, no.
That says 5x instead of 5 to the x. I don't think any of them are right.
That one,
Right there.
Which one?
the fourth one down.
Fourth one down? It says plus 4, there's the one.
Ah.
All right, who had that? Derek and Chris. All right, good job. All right,
Two people are gonna pass.
let's go. Yeah, this is not making me. All right.
We quiz next week?
What? All right, let's look at this one. Listen up now. Natural log of 4x. 1 over 4x times. You have to kick out a 4. You have to now. Somebody a minute ago asked a question about what is we have to kick out or multiply out. Did somebody ask that?
Ask which ones do we need to do?
Okay, ask that again. You still have that question?
How do we know when to take out numbers and when not?
Any time you've got a number multiplied by the x inside of the function. So, what does inside the function mean? Well, it's easy with sine or cosine to see what's inside, right, in the parentheses. With e or an exponential, it's anything that's up in the power, okay? With a power rule, it would look like this. If you had 3x plus 2, if you had 3x plus 2 to the 5th, then the derivative would be 5 parentheses 3x plus 2 to the 4th, and Harry, we'd have to kick out what? We'd kick out a 3. Because the 3 multiplied on the inside compresses the graph and changes those slopes by a factor of 3. Okay? So in a sine or a cosine, it's easy to see what's in the middle. With the natural log, it's easy to see what's on the inside. E to the something, it's anything that's up in that power is considered the inside of the function. And if it's a power rule, it might look like this. You have to kick that out. Okay, so in this case, the interesting thing about natural log is that those actually ends up canceling. And you end up with just 1 over x. Plus, what about log base 3? 1 over natural log of 3. Okay, that's just what the rule says if it's a base other than e. Plus, what's the derivative of ln2? This is the one I was trying to fool you with on Friday. It's 0. It is not 1/2. ln2 is just a number, like 7 is a number. The derivative of 7 is 0. The derivative of ln2 is 0. There's a big difference between ln2 and lnx. lnx is a function. The derivative is 1 over x. ln2 is a number. The derivative is 0. Okay? Now, for time, we're not going to do quite as difficult of antiderivative one here. Oh, whoops. But let's do this, okay? So we'll start here with f prime, and I'll put up who put what answers for that over.
Yeah, you don't
But
need
all right. So for this one, let's do this. 3x to the 5th minus square root of x plus sine 3x. Okay? You find f of x. So we're doing the antiderivative here. Or I might just give you a function f, and the directions would say find the antiderivative. Probably would say find the general antiderivative, because really this is like an initial value problem. Or excuse me, it's like a differential equation. F prime, you're finding f. Right? Really, this is a type 1 differential equation right here. And we're solving it by doing the antiderivative. I didn't give an initial condition, so yeah, we had a whole bunch of people in the last one put 1/2, didn't you, on the last one? So, okay.
And then 4x underneath.
But it looks like, what would it be? Nicolette, Seth, David.
Yeah.
Other Davids. Other David. You typed it in. It's okay. It's not submitted yet. And then it came up right as you were.
Is there like no point in me doing this then?
No, it's not submitted, so you can still go ahead and change it. You can still go ahead and change it.
Trying to get out of it.
Again, antiderivative is more of a guess and check. Antiderivative is more of a kind of, I think it would be this. Let's do the derivative of it and see if it gives me what I want.
Because when you write it, you got the 3, it has to be 1. I don't know if antiderivative is
You know, that I still would say.
Yeah, this one of my calculators did. Well, it wasn't that low, so I don't know why There's 3 separate. My fingernails don't too long.
Yeah. That's good. I don't think it kicks in that.
All right, let's go through this.
Wait. Let me finish.
So the first one, the power rule, we said, I mean, because again, common sense would say, well, when you do the derivative, you drop the power 1, so it makes sense the antiderivative will have to be there. Okay, but we actually kind of had a rule for these, and that was that the 3 would just kind of stay there, raise that up to a 6, divide by 6. Now, as you simplify that, of course, that's 1/2 x to the 6. But most importantly, this is the antiderivative because when I do the derivative, I bring the 6 down in front. 6 times 1/2 is 3. Drop that to a 5, I get 3x to the 5th. That's really why that's the answer. Same thing on this one. We know the rule says bump it up 1, which would be x to the 3/2, and divide by 3/2. What do you get if you divide by 3/2? You multiply by 2/3. But again, your check should always come next. You should say, well, if I brought the 3/2 down in front, times 2/3 would make 1, x, and then drop that by 1, x to the 1/2. Okay, finally, antiderivative of sine. Cosine, but is it negative or is it positive? Well, the one to always remember is derivative rule. The first one we learned was derivative of sine is cosine. You should be able to get everything from there. If the derivative of sine is cosine, then the antiderivative of cosine has to be sine. It has to go back the other way. So those are the ones that are positive. Derivative of sine is cosine. Antiderivative of cosine is sine. Well, this one's the antiderivative of sine, so it's got to be negative cosine. And what about the 3? Well, if we're doing the derivative, it'll kick out a 3. Okay, now you might say, well, antiderivative kick out a 1/3. Well, we got to be a little careful about that. But with constants, yes, that's essentially what happens. Later on, we'll be getting into something else with something other than constants. We got to be careful with that. But what'll happen is this ends up being negative 1/3 cosine 3x. Now again, if you say, well, where did that 1/3 come from? Well, you would have seen it with the check. Because you just said, all right, the derivative of cosine is negative sine, which would cancel out that negative. The inside always stays the same. We'd had to kick out a 3. Well, it's a good thing the 1/3 is there, because if I kick out the 3, I need something to cancel it, because there ain't no 3 out there. So I need the 1/3. And then don't forget the plus c.
But we couldn't submit that.
Don't forget. Seriously.
I couldn't submit that. I put plus C in there. I was trying to go to submit syntax error.
It wouldn't let you put a C?
No.
Yeah, that's what happened to me.
Yeah.
So can we just hit plus X? Hey,
Alright.
can we just do plus X?
Nah, yeah, go ahead. That's fine. All right. Well.
Why does he keep saying syntax error?
Yeah.
Oh.
Like
most of the class.
Okay, but that one's right, that top one, right?
Other than the C.
Other than the plus C.
Why keep saying syntax error? Where's that?
16.
16. So,
Mine looks just like that one.
all right, let's move on, because out of 30, let's keep going, because out of 35 points on the quiz, that's probably about 10 of them, so it's important, but there's a lot of other stuff here. So, let's let's keep going. Let's keep going with the differential equation stuff. And let's look at page 131. This was the Torricelli's law problem. This is on page 131.
But you get the answer.
All right, now. Okay, let's focus in here now. When it comes to the differential equation stuff, now earlier we kind of went through this. We did an initial value problem. This is one in a story problem setting. Now, this is one of type 3. The square root changes this. This is not an exponential growth one because that shouldn't have the square root on it if it was going to be. So what they did, and we started this in class on Friday, we got through some of it together. They told you this was the solution. Now again, Y here's the depth of the liquid draining out of the tank. T is the time. C and K are the two unknown constants in this problem that we don't know. All right? Sometimes we have one unknown constant, but sometimes there's more than one. And that's what we have here. Now, the first question A, and we talked about this the other day, of when is the water rate dropping the fastest? You'll probably be asked a question similar to that. If I give you a story type problem on a differential equation, here's what the variables stand for. I want you to be able to answer a question where you have to interpret the differential equation. All right? Now, one question in this one could be the one they asked. When is the water rate dropping the fastest? We said when it's full. Because the bigger Y is, which is the depth, the bigger Y prime will be. And Y prime is the rate. So it'll be dropping the fastest when Y is the biggest, when it's full. Okay. Another question here could be this. They said that K is positive. Right? In the right before problem A there, they said K is a positive constant. I might ask you this. Why is K positive? How do you know in this problem K has to be positive?
Otherwise it starts filling up.
Okay, say that. Shh, guys.
Because if it's negative, then it'll start filling up instead of going down.
Say, expand on that. That's not enough.
Since that's subtracting K, if it was a negative, it'd be adding K. I don't. Never mind.
You're right. You're right, Devin. You're on the right track. We just need to let's make it so everybody understands what you're saying. Somebody want to expand on what he's saying, Chelsea?
If it was negative, it would be a negative times a negative, and that's a positive. So if it was positive, that means it's filling up.
Wait. Okay. Both of you are saying it's. What?
The tank.
The tank. Okay. It has to do with Y prime. That's what you guys are missing. You got to tell me something about Y prime. The rate, let's think of the chart. Okay, Y is the depth, that's the top row of the chart. Y prime is the second row of the chart, right? This thing, the tank needs to be emptying, which means Y is doing what? Y is decreasing, okay. Y needs to be decreasing. Since Y needs to be decreasing, what's that tell you about Y prime? Okay, that's a part I wasn't hearing anybody say. In this problem, Y prime has to be negative for Y to be decreasing. That line, you would need to say that, okay? You guys were on the right track. We're just not saying it right. So Y prime has to be negative in this problem because Y is decreasing. So if Y prime is negative, that means this side of the equation has to be negative. Now let's keep going. I also didn't hear anybody say anything about square root Y. What's square root Y have to be? Because Y is a positive number, and you do the square root of it, that's positive. So a description along with something like this, you have to talk about all parts of the equation. So square root of Y has to be positive because Y is the depth, it has to be positive. Y prime has to be negative because Y is decreasing, so therefore Y prime has to be negative. All right, we already have this negative in the problem, So what's that leave us for there to be an equivalence here? What's K got to be? K's got to be positive for the two sides to both come out negative. That would be the description I would want you to say. Okay? All right. What, let's see here. All right, well, that's something along those lines. You need to be able to look at a differential equation and be able to talk about y and y prime in those chart terms about increasing, decreasing, positive, negative, and be able to understand about what it's saying. Okay? All right. Next thing that we went through kind of B, we verified that this was a solution. We did a T-chart here. We got several of those on the videos. We did a bunch of those the other day. So I won't take time again today to do that. But be able to verify. So you would just take this and plug it right there for y. And we'd have to do the derivative of this and put it over there for y prime. We did that Friday, right? We got that far on B. And we had to kick out what when we did this derivative? You bring the 2 out in front. What do you got to kick out? Negative k, because there's a negative k multiplied times a t there. Okay? So anyway, we verified that this was a solution. Then the next part, and this was what many of you were working on. The next part is where this became an IVP problem. They told you at y of 0 was 9 and y of 20 was 4. Now what did that mean? What does this mean? Times 0, 9 feet of water in the tank. At 20 minutes, I think, are the units. 4 feet of water in the tank. So we know this tells us something about how fast it's draining. Now we needed 2 initial conditions because we have 2 unknown constants. So now the next step is to do exactly what we did earlier today when we went to find those. We're going to plug 0 where? In for t, and we're going to put 9 in for y. So it'll look like this. Luckily, that makes the k disappear. Sometimes what happens here is you end up with 2 equations with 2 unknowns. You have to solve one of them. You know, if we'd have had an equation here that c and k both in it, we'd have to solve one for c, plug it into the other one, and get it that way. But this is going to work out nice. So we're going to get 1/4 c squared. We're going to multiply the 4 over there, get 36. We're getting c equals 6. Now, I just made a terrible, terrible mistake right there. Plus or minus. Now, a lot of you just forgot that, and you ended up getting lucky because the negative one isn't going to work anyway. Okay? They did say this in the problem. C minus KT's got to be greater than or equal to 0, they said, for physical reasons. In other words, so the tank's draining other than filling is really what that means. Well, that means C's got to be greater than or equal to KT. Now remember, we already said K was positive and T is positive. In this problem, it's time, and they told us we're only going to deal with positive time values. So since this side's positive and C's got to be greater than that, then C's got to be a positive. Okay, so that's how we know we don't need the negative there. All right, now, what you should get in the habit of doing, and this goes back to something we said at the beginning of class today. We're not done there, and we didn't solve. Yeah, we solved for C, but the solution, remember, to the differential equation is this thing. So I should rewrite this now with my 6 now in there for the C. Right? This is the part people get confused on, especially when there's 2 unknown or 2 initial conditions. You always come back and take the general solution and then you plug that, put that C back in. And then this is what we have. Now I'm going to take the next one. I'm going to put a 4 in for Y. And I'm going to put a 20 in for T. Right? And I get this. So now we multiply the 4 over to that side. I'm going to square root both sides. Now right there, I should have done a plus or minus again. Okay? I should have done a plus or minus right there when I did the square root of both sides. However, this 6 minus 20k, that is my C minus KT. That is, okay, because 20 is in place of the T and 6 is in place of the C. So this is my C minus KT, and we said C minus KT has to be positive. So therefore, it can't be the -4, so we can leave it off. All right, so we subtract 6, which is -2. We get -20K, so we get K equals 1/10. What should I write down next? What should be the next thing I write? I should write the formula one last time. 1/4 6 minus 1/10 T squared. There is my solution with C and K found. And now I can go on and they say, and at this point then I can answer all kinds of questions about this particular situation. Now the one they want to know is at 60 minutes that it's empty. Show that it's empty at 60 minutes. Well, you would do what? Plug in 60 for T. 1/10 times 60 is 6. 6 minus 6 is 0. Y equals 0. The depth is 0. But they might have said, how deep is a tank at 40 minutes? So you'd put a 40 in for T. They might have said, when is the tank 30 feet deep? You put a 30 in for Y and you'd solve for T, right? So there's a whole variety of questions we can then ask after we've got the solution for the tank problem. And they would all involve using the solution. That's why the solution is important, because it'll tell us all about the tank. Now the question they did ask was, what time is the water level dropping at 0.1 feet per minute? Well, where's the 0.1 got to go into? That's Y prime. So then I've got a choice. I do have Y prime right here. The problem with that is if I solve, I'll be solving for Y, not for T. Well, I could find what Y is, then I could come over to here and put it into this one for Y and solve for T. Or I could just do the derivative of this one, right? You could do the derivative of this. Bring the 2 down in front. You'd have to kick out a -1/10, right? Because it's multiplied in there. But you could do this derivative, Y prime, and then plug your 0.1 in for Y prime. With one little important piece, though. You wouldn't put in 0.1 for Y prime because the tank is dropping. We said this. You'd have to put in -0.1 for Y prime. It says, at what time is the rate dropping 0.1 feet per minute? Remember we said earlier, Y prime has to be negative. So yeah, it is tricky. So you'd have to put a -0.1 in for Y prime to solve that correctly. Okay. So that gives us a lot of different things to do, especially regarding the differential equations. Let's see. Max-min problem. I'm trying to think if there's anything else with differential equations. We talked about verifying a solution, the T-chart idea. We talked about the initial value problem, which is what this is really. You got an initial condition, plug it in. You are going to make sure you look over this one. This was like number 48 on the other in section 2.6. Or 40, excuse me, it was 47. That was a homework problem we had, number 47 on page 139. So I want to make sure you're looking at that one. That was where you were given this differential equation right here. Although you were actually given it, it looked like this. Pretty good bet you're going to have something to do with the exponential growth differential equation. Okay, that's the differential, that's the exponential growth differential equation, the one that goes AE. Okay? Probably not going to do one like 48 just because of the time it takes with all the different parts, and we didn't know the solution, and we had to verify it was a solution, and so forth. But one like 47 on page 139 would be a good one to go revisit and look at again. Okay? That was on our homework on Thursday, I believe. And that was where you use the memorized one. it's very much like number 48 we just did. The difference there is they gave us that solution. Talked about this idea of being able to discuss a differential equation. What about yeah, I think look at 49 on page 131. Let's just do that real quick, and that'll leave us just enough time to do a quick max-min problem. On page 131, number 49, a small town charity fund drive aims to raise $65,000. According to Alfred E. Newman's law of cooling of enthusiasm, ever heard of Alfred E. Newman? You have to Google it. Alfred E. Newman's law of cooling of enthusiasm, the rate at which people contribute to a drive is proportional to the difference between the current total and the announced target amount. Let Y be the current total in dollars T weeks after the start of the drive. So what you might be asked to do is be able to write a differential equation, okay, that represents a description like that. So let's read that sentence again. The one that says the rate at which people contribute is proportional to the difference between the total and the target amount. Now, why is the amount contributed? So what would be the rate that they contribute? Y prime, right? So the rate that they contribute, Y prime, is proportional to, now this comes from science class, and we talked about this yesterday. What do I put down when I read that? Is proportional to, or directly related to, that's the K value, okay? In the one we memorized, Y prime equals KY, what I said the other day is that says the amount of money you have in the bank is directly proportional to the amount, or excuse me, the rate your money grows is directly proportional to the amount you have in there. So that's Y prime equals KY. Okay, the amount, or the rate that it grows is proportional to how much you have. This one says that the rate that people contribute is proportional to the difference. And what difference do they say? Current total and the target amount. In that order do they say it? So what do I put for the current total? The current total was Y, and the target amount was 65,000. Now let's see if that makes sense. Think about what we did with the Torricelli's law problem. When would they contribute the fastest? When would the rate of giving be the most? It would be when this value is the biggest, right? This side will be the biggest when this side's the biggest. Well, when will this difference be the biggest? When Y is, wouldn't this be the other way around? Because Y minus the current total would be less than 65,000, right? So that'd make that negative. So we don't want that. So we want 65,000 minus Y. There we go. So because we want that to be positive, because right? Because Y should be increasing, right? With the amount we're raising should be increasing. Okay, so it should go this way. So when Y is the smallest. Now, does that make sense? It's Newton's law of cooling of enthusiasm, right? At the beginning, when there's not much to, when not many have given, people give the most, maybe. Now, you could argue with that. As they get closer, why would it slow down? Why would the rate get less as Y gets closer to this, making this smaller? Well, most people have contributed, maybe. The people that are going to contribute. Now, some people might say, when you get close, everybody gets excited to see it go over the top, and maybe people give more. That could be, maybe at the very end. But according to this, again, whether this is right or not, but according to this, this would say the rate of giving is most in the early stages. But mathematically, that would be true here, right? Because this would be biggest. Okay, but be able to just take that sentence. The key word there for proportional, and understand you just throw a K in front of it, right? And that's the proportionality constant for that problem. So just, I mean, that'd be a 1-point problem or something like that, where you could just be able to just take those words that involve rate and derivative and be able to put that into something. Okay. So I've got a quick little problem we can do here for a max-min kind of a thing. We've done many of those, and so you've got all kinds of ones of those you can review. But let's take this function here. Let's take f of x equals 3x to the 5th minus 25x to the 3rd plus 60x. Let's find local max min. That's good enough. Let's find local max min on that function, because that'll give us practice enough. Inflection point would be the same thing, but with second derivative, set it equal to 0. Do the number line. Okay, but this one is going to be stationary points, do the derivative, set it equal to 0, number line. Okay, go ahead and try that real quick. Did you get it? You know how to do the derivative? Okay.
I almost got it. Yeah, okay. Yeah, okay.
That's what I was trying, but it's not working.
I just thought stupid. That's why you came up with it first.
All right. On before we take a quick look at it, if you're finishing that up, go ahead and keep doing it. I'm just writing up some problems out of the review. The review problems are, there's some good ones in there. Like I'm picking out some of these. The REV here means the review problems. So those are good, but also you want to spend some time going back through these things we've talked about here today. I'm trying to pick out a few from the homework. I mentioned a few, like here's this 47 on page 139. Any of those problems where you have to verify that something's a solution with an initial value problem. Anything, this 47 uses the one we've memorized, so I wanted to throw that one in there. So all that stuff we've talked about today with differential equations that you need to be able to do. And then as far as the chart, the one thing we didn't get to today, but we spent a lot of time on that, and it's in the video from Friday, is the calculator, using the calculator on the trig max-min problem. Okay, now here's another one that you could do. Today you had, in section 2.7, today you had number 45. That was a calculator max-min problem. You could also do number 46. Today, for a no calculator, I had assigned you number 41. That's a no calculator problem with trig, so we didn't get a chance to go through the trig stuff today, but we've done that for a number of days last week. So there really was nothing, new to do there. But those are certainly some that you could practice the trig max-min stuff on. Okay? Now, on this one, I think we've done a function very much like this earlier. You factor out a 15. You got this.
It's x cubed.
X squared there. X squared, there we go. And now we've got x squared minus 4 and x squared minus 1, which gives us plus or minus 1 and plus or minus 2. And then we need to put a number line. Right, like this. Okay, and what did you get? Out here you get right? So max,
You would spin the other
min, right? Now, listen up here now, listen up. I know you're in a hurry to get to Bearcat time. But, oh, we don't know. Wonder everybody's in a hurry today. All right, guys. All right. Wait, time out. The quiz is a little important too. I know lunch is also, but big plans today. What do you have to do when you write a local max or min? You have to write out why. You have to say, this is not good enough for the max-min answer. You'd have to say, this is a max because f prime changes positive to negative, so f changes increasing to decreasing. You have to say that. You have to connect those. And if that was an inflection point scenario, you'd have to say that these are inflection points because f double prime changes positive to negative, so f changes concavity. Since I don't have Bearcat time either, just leave the hat sit on your desk so you can get out of here a little faster.
another day of sitting and waiting. Yeah. He wants Chinese. What?
Or you just go somewhere, can't you drive?
Yeah.
What are these two?
What?
What are these two?